All right, so this is our last section, and also the second set of applications for exponential functions. And these are models you use in physics, chemistry, science, particularly biology, because a lot of things in biology have exponential growth as well. It's not just money and interest. For example, cells, bacteria, those change exponentially. Radiation, or the amount of radiation in certain objects, that decays exponentially. Okay? And so all three of these things obey what we call the law of uninhibited growth or decay. And if you look at here, that is if A of t represents the amount of something. That something could be number of cells, it could be the size of a bacteria colony, the amount of radiation, or the amount of some element in an object. That represents A of t represents the amount at time t. A0 represents the initial amount, and k is just a constant. And that k is really going to determine the rate of change of this function. So if k is positive, we're talking about growth. If k is negative, we're talking about decay. And you can see that this actually is of the same form of the continuous compound interest. We have a constant times e raised to another constant times t, right? So instead, in a way, that formula was a special case of this, where p0 was really a0 and so on. So that's one type of function that we'll be looking at. The other thing is another application of exponential growth and change is Newton's law of cooling. When we take something out of an oven, it cools, but it does not cool in a linear fashion. It cools exponentially. It cools it cools in a way that the temperature gradually approaches room temperature. And that's what Newton derived this formula from. If U of t represents the temperature of a heated object at time t, and U0 represents its initial temperature of this heated object, and capital T represents the temperature of the surrounding medium, which is basically like room temperature, and k is a negative constant, then U of t is going to obey this rule. And we kind of see that this makes sense. We can, because we know things. The temperature of an object is going to approach room temperature as we go along. So it's going to the curve is going to look like this. Okay. So we're just going to be using these two models for this section. So really, the best way to do this is just look at the examples and look at the problems, and just like in the last section, identify what letter or what variable you're solving for. So in this case, the size p of a certain insect population at time t obeys the law of uninhibited growth, and we're given this formula. So in this case, A0 and k are already given. The initial number of insects, well, we can see right here it's 500, but if we weren't sure, we could just plug in t equals 0, and that would be 500 times e to the 0.03 times 0. So this would just be 500. The growth rate, that's just the k part, right? The growth rate is k, which is 0.02. Population after 10 days, well, we plug in t equals 10. So this would be 500 times e to the 0.02 times 10. And then we use our calculator to find that this is in fact 610.7. Okay, we can round to one decimal place. That should be okay. When will the population reach 800? So you're asking for what t. When means you're asking for t. So we want to find out, well, what's the value of t when this is equal to 800? All right. So we have this type of equation that we want to look at. Okay, this is an exponential equation. Our unknown is part of an exponent. If you recall, we isolate this power of e, so we can do that by dividing both sides by 500. And this reduces to 8/5, and that's equal to e to the 0.02t. And then we can either take the natural log of both sides and simplify it, and that will tell us that 0.02 times t is in fact the natural log of 8/5. And so t is going to be the natural log of 8/5 divided by 0.02, okay, which is 23.5 days. Okay. When will the population double? This is what we want. We are asking for t, and when the population doubles, our initial population was 500, so we'll find the t when this will be equal to 1,000. Okay. And then we proceed as before. We can divide both sides by 500. We'll get 0.02t is equal to the natural log of 2. And so this turns out to be, t is going to be 34.7 days.